Robots have to face the real world, in which trying something might take seconds, hours, or even days. Unfortunately, the current state-of-the-art learning algorithms, for example deep learning, either rely on the availability of very large datasets or only make sense in simulated environments. The scarcity of data calls for algorithms that are highly data efficient, that is, that minimize interaction time between the robot and the world. In reinforcement learning for robotics, model-based policy search algorithms are the most data-efficient ones. After each episode, the algorithm updates a model of the dynamics, and then it searches for the best policy according to this model. One way of increasing the data efficiency of these algorithms is to use priors in the dynamics models. One of the most traditional ways to do so is model edification. Most approaches for model edification rely on two main ingredients. First, proper excitation of the system, which can be very time consuming and error prone, and secondly, parametric models. However, these approaches assume that the analytical equations can fully capture the system, which is often not the case when there exists a real model mismatch, like for example when the robot is damaged. We propose a new Gaussian process learning scheme that combines model edification and non-parametric model learning. We formulate it in a way so that we can elegantly learn it with maximum likelihood estimation. We call this model learning procedure Gaussian Process Model Edification, GPMI for short. We combine GPMI with the Blackdrop's policy search procedure in order to showcase its effectiveness. We first evaluated our approach in simulation with a pendubot swing-up task. We compare 7 algorithms, including ours, with 4 different priors. Blackdrops with GPMI always solves the task and achieves high rewards at least as fast as all the other approaches, including model edification and state-of-the-art policy search algorithms with or without fixed priors. We also evaluated our approach on a hexapod locomotion task with a physical robot, where the robot has to walk as fast as possible despite being damaged. In the initial episode, the robot optimizes the prior model and executes the obtained policy. As expected, the performance of this policy is not very good because of the damage. During the episode, the robot collects transition data that are used to improve the dynamics model using our new GPMI learning procedure. After only a few iterations, the robot already starts to work faster and straighter. In just 5 iterations, we get a high-performing policy despite the severe model mismatch caused by the damage. Blackdrops further optimizes the policy, and the final policy is a highly effective walking gait that was obtained with as little as 28 seconds of interaction time.